All right, let's get started. Welcome to this session on testing of database and low-level software. I'm Michael Pradl from the University of Stuttgart and have the pleasure to chair this session. We have 7 exciting talks, and the first one, just come up, will be on compiler test program generation via Memoized configuration search, and this talk will be given by Chenyao. So.
Hello, I'm Chenyao from Tianjin University, and I'm to be a doctoral student supervised by Professor Junjie Chen. I present our new work on compiler testing, compiler test program generation via Memoized configuration search. Compilers are one of the most fundamental software, and almost all the software is required to be processed by compilers before we use them. However, like other softwares, compiler can also contain bugs, and this bug may be very harmful due to their fundamental role. On one hand, compiler bugs can cause any software built on them to produce unexpected behaviors, and on the other hand, compiler bugs can confuse the software developer and aggravate the debugging difficulty. So it's important for us to ensure compiler's quality. To ensure compiler's quality, many test program generation works generate a lot of test programs according to the test configuration. A test configuration consists of a series of options, and each of which controls the corresponding program features probabilities in the generated test program. And so we can generate a diverse test program via the exploration of diverse test configuration. Some of the existing approaches infer a set of test configuration from the historical data in an offline way, while the effectiveness is usually limited by the many history information, and some approaches randomly construct the test configuration during the online search process, while they can hardly capture the useful information for elaborate coordination among options. To relieve the above limitations, we propose our approach, MCS. MCS adopts the online configuration search to map the information of the compiler version under test, and it adopts the Memoized configuration search to construct the next configuration according to the explored configurations. And to see the mutual effect among options, we adopt the multi-agent reinforcement learning and design its reward through 3 perspectives. As we mentioned before, MCS adopts the reinforcement learning, and the reinforcement learning aims to obtain an optimal control policy for each agent that interacts with an unknown environment. The target is to choose a sequence of actions that can maximum the cumulative reward in a long run. In our case, the test configuration is regarded as state, and the action is the configuration change. And to see the mutual effect among options, we assign each option an agent to separately and flexibly determine the action. MCS adopts the overall process of the reinforcement learning, and it consists of 4 steps. The first step is the action selection. Each agent will select an action according to the home test configuration, and the next step is the environment transition. MCS will update the current configuration according to the action selected in the first step. And so the next configuration is constructed by MCS. And the third step is the reward measurement. MCS will use the next configuration to generate a lot of test programs for compiler testing and calculate the reinforcement learning's reward according to our predefined reward function. And this is the most important step in MCS. And the last step is model update. MCS adopts the D-step update strategy and will update the model after D consecutive actions are predicted for all agents. And the reward measurement of MCS mainly consists of 3 parts: the extreme value punishment, diversity measurement, and the bug triggering award. And the key component is diversity measurement, so we will introduce it first. The diversity measurement aims to explore the configuration with the different test capabilities. Actually, the test capability of a test configuration is reflected by the programs they generate. So we use the extracted program feature vector to represent the test configuration, and define the distance between 2 test configurations as the constant distance between two extracted program feature vectors. And to reduce the influence of outliers, we will calculate the diversity measurement for each test configuration, and it is defined as the average distance between the current configuration from a set of closest explored ones. And finally, the diversity reward is defined as the average diversity improvement from the current configuration over M configuration within the closest time. And MCS may meet some test configuration regions that can generate a lot of timeout test programs. These timeout test programs will greatly slow down the testing process, and it is harmful for computer testing. And as we introduced before, the configuration option controls the corresponding program features probabilities, and the extreme value option may lead to lengthy generation time and the generation of a program run for a long time. So we conduct a preliminary study to investigate the relationship between the generation of timeout test programs and the extreme value options. And the result shows that the more extreme value options are set, the more timeout test programs will be generated. So we design our extreme value punishment to prevent MCS from the exploration for timeout ones. And to generate more bug triggering test program, we design our bug triggering award to tell agents what combination of option is better and what region of the test configuration deserve more exploration. And the reward and the bug triggering award is calculated according to the number of bug triggering test programs and lead to more exploration on the bug triggering test configuration regions. And to evaluate the effectiveness of MCS, we conduct a series of experiments to answer the following research questions. To answer RQ1, we conduct 10 days testing on GCC and LVM, and we choose both offline and online sorter approaches as our baselines, and use the differential testing to determine whether a compiler bug is detected. This is the result of the number of detected bugs. MCS outperforms two baselines, and that demonstrates the effectiveness of MCS on bug detection. And we also evaluate the number of unique bugs. We can find that MCS detects most of unique bugs, and more than half of bugs can only be detected by MCS. But we can also find that some of unique bugs can only be detected by baselines. That may be because the high count focus on a certain portion of test configuration and make further exploration on it. And some testing may explore some regions that MCS didn't. And MCS has also detected 16 new bugs on GCC and LVM's trunk version, which demonstrated that the effectiveness of MCS on the latest version of compilers. RQ2 aims to investigate whether the extreme value punishment and the bug triggering award are helpful for compiler testing. We designed 2 runs of MCS and conduct them to test the subject for 10 days. The result shows that MCS still outperforms 2 runs, and it demonstrates that both components benefit the compiler testing. And we can also find that 2 runs still outperform the baselines. That shows the component of diversity measurement can still get the search process and lead to suboptimal result on 2 runs. To summary, in this paper, we propose our novel test program generation approach, MCS. We adopt the reinforcement learning and design its reward through 3 perspectives, and evaluate the effectiveness of MCS and its 2 reward components. That's all my talk. Thank you.
Yeah, thanks a lot for the talk. Time for some questions. Okay, while you're all still thinking, maybe let me get started. So one of the rewards is for triggering a bug. So one of the rewards is this bug triggering award.
Bug triggering award.
Yeah. So how do you make sure, or how do you identify duplicate bugs? So if the same bug is triggered multiple times, do you still give a reward for that?
No. Identify duplicate bugs during the testing process may lead to the large time cost. so we didn't so we don't deduplicate the bugs in the bug triggering award.
Ah, okay. So if the if csmif triggers the same, generates a program that triggers the same bug multiple times, you will still
it will calculate twice.
Okay. Ah, I see. Okay. Any other questions? Yeah.
Thanks for your talking. I want to know which language features are you extract from a given program.
Oh, let me see. Oh, I may forget it. Here, the variable types, the type of statements, type of operators, and the type of and the qualifiers. According to the time of occurrence time of the corresponding program features, occurrence time.
Does this data sensitive, or you do not care the data or not?
The data?
For example, if the statement contains some constant, you extract them or not?
No.
Okay. Yes.
I don't consider it.
Who else has questions? So we had one question here. We have not yet seen a question here. Oh, yeah.
Thanks for your talk. May I ask a question about the duplication of the bugs? Based the duplicated bugs for your study. If two bugs are, the question is followed by the chair. So there are two kinds of bugs. One is run code bugs, another is crash. I think for crash, it's easy to identify whether two bugs are the same or not. Curiously, how did you identify two run code bugs are different bugs or the same bugs? Thank you.
I can answer this question from two perspectives. For the bugs on the historical version, we use the correcting commit technique. The correcting commit finds the first commit that makes the bug triggering test program pass, and it is identify the correcting commit. If two bug triggering test program find the same correct commit, we'll see these two test programs find the same bug. And for the bugs detected on the latest version of compilers, we'll report them to the developers to identify them.
Yeah, I have a clarification question. Thanks for the presentation. So maybe I missed it. So how long did you run the testing campaign, and especially for the reinforcement learning part, for the training part, learning the policy? So how much time did you devote it for the policy learning, and how much time for the testing overall?
Almost all the time is for testing, for the evaluation of the test configuration. Because once a test configuration is generated, we will use this test configuration to generate a lot of test programs and use this test program to test compiler. So it is the most time we spend on it.
But time-wise, horizon, like weeks, days, months. So how long did you run the evaluation part of your paper?
I don't evaluate the time cost, but the most of time spent on the compiler testing. Less time for learning.
Yeah, but I mean for finding these bugs, how much time did you take? So how much time did you take to find these bugs in terms of like running the tool and
for new bugs?
Yeah, I mean overall. So how much did you run?
About 3 months.
Okay, thank you.
All right, well, thanks for all the good questions. If there are any more questions, I guess we need to take them offline because we need to move on. But yeah, thanks a lot for the talk. And then
Is it good now, or is still seeing the notes?
No, this looks good. We can see you and your first slide. Cool. Yeah. So the next talk is going to be given by Cong Yan. Is that you?
Yeah.
All right. Yeah. On generating test databases for database-backed applications. So please go ahead.
Cool. Thanks for the introduction. Hi, this is Cong, and I'm from Microsoft Research. So today I'm going to talk about work on generating tested databases. Okay. So in this work, we mainly focus on database-backed web application. So this application architecture, they usually have a server and a database. So when the client sends an HTTP request to the server processes the request, sends SQL queries to the database to fetch persistent data. It composes this data into a web page and it returns it to a client. So the test for such application often involves two parts. This is a simplified test on the checkout page of a shopping app. So the first part creates a test database with a carefully designed content. So each line here calls a create function to insert a tuple into the database. Then the tester calls a post action with this URL because it's a web application. So the carefully designed database should respond with a successful checkout with the matching UID and order ID in the URL reflected on the this line. As one can imagine, because the web page is generated from the content retrieved from the database, many branches in the application would be database dependent. So here's an example which checks whether there's enough inventory for each item to be checked out in order. Such branches are actually pervasive in the application. Over half of the branches are DB dependent in the applications we studied. So currently, all the tests for are manually designed by developer. Even with substantial effort, like some apps, there are up to thousands of manually designed tests. The branch coverage is still low, often below 50%. So can we automatically generate tests to increase the coverage? To generate tests, the key is to generate the database content. Like in the example, we can create a database with insufficient inventory, which leads to a failed checkout. So there are two major challenges. The first is the efficiency. The search space is usually very large, including tens of tables and several hundreds of fields. Not to mention, each table can have multiple tuples. These tables are often not independent. Fields are often correlated with foreign key or one-to-many relationships. So only a few states in this vast space is useful, meaning that they will increase the branch coverage. Furthermore, running the test can be very slow because it needs to connect, populate, and query the database and render the web page. So each test can take up to from 8 to 28 seconds to finish as we experimented. The second challenge is that not all DB states are valid. Usually the data is programmatically inserted into the database, which usually goes through some checks. Like before the order is submitted, the application checks the order that has some items and the emails is not blank. So any database with an empty order or order without an email would not be possibly seen by the application. Such check implies certain data constraint, which is also pervasive in the applications. With so many constraints, generating a database satisfying all of them is very challenging. So we propose DB Griller. DB Griller tackles the validity challenge by constructing a constraint checker from rewriting the validation code. It tackles the efficiency challenge by first propose a few mutation mechanisms that can produce DB state candidate that is likely to be valid, but still diverse in the sense that it can help increase the branch coverage. Second, we propose branch projected view. This view is used to aggressively filter DB states and only keep those that are likely to be useful. With this, eventually DB Griller produces a small number of valid DB states that can achieve good branch coverage increase. We first look at the constraint checker. Applications are built with ORM frameworks like Ruby on Rails, and they often use callback mechanisms to validate the data. So DB Griller simply collects all the validation callbacks and rewrite them into a constraint checker. It includes an optimization to remove irrelevant constraint to make the constraint checking more efficient while pertaining more useful states. Now let's look at the mutation mechanisms. We leverage the existing database designed by the user and mutate them to get more DB states. We have 5 mutation mechanisms like mutating table fields, delete tuple, one tuple, merge multiple DB states, using the DB states designed for other tests and also mutate the DB states by running the test. So empirically, these mutations changes the database states in a relatively structured way and are likely to be valid compared to just a pure random mutation. And meanwhile, they are also diversely change the field values and the tuple relationships, which are often used in branch conditions. These mutations can generate a large number of DB states, so we filter them with branch projected view, keeping only states that are likely to be useful. To compute the view, we first do branch analysis to figure out variables associated with the database. In here, actual type is crucial because in the ORM, the type tells which table this variable is read from. So the challenge here is to figure out variable types correctly for a dynamically typed language like Ruby. We tackle this challenge by combining static and dynamic analysis. Static analysis is used to find out which variables and classes are involved in the branch, like the item table, and which field is involved, like item.inventory ID. And then we run the existing test and check the type of these variables. Like running the branch, we inspect and get the item variable is of class line item, therefore mapped to the line items table. Then we continue to figure out what data from the database is indeed being used in the branch. Because the variables is essentially stored database query result, so we need to associate queries with the variable used in the branch. Sounding easy, but this is actually very challenging. We can only use the query log to get the queries issued, but this does not tell where they are issued in the application. So we simply compute a conjunction of the query log and the branch view. The branch view includes which table and which field is used in the branch, as we see earlier. So here the log has 3 queries, and then the branch view includes inventory table and the 2 fields from the line item table. Taking the conjunction of these tables and fields with the query result, we get this branch projected view, which is a subset of the query result. Then we use this branch projected view to filter candidate DB states and only keep the states that have different view. Because running the queries and comparing the results can be very slow, so we include a few optimizations to accelerate this, like running the query purely in memory with SQLite and compute the hash value for each view instead of comparing the full query result and focus only on uncovered branch instead of all branches. So that's all about the key components. So let's look at the evaluation. We evaluated on 9 popular open source web apps we built with Ruby on Rails. We measured the efficacy by the coverage increase of DB-dependent branches. With our method, we can cover up to 30% more branches and making the overall coverage reach up to 80%. Overall, it takes from 8 hours to 120 hours to achieve this. We have a time limit cut at 120 hours. This is because running each test on a new DB state is very slow, taking up to 28 seconds, and validating the state is also very slow. So in this time range, we only produce 96,000 new DB states to increase the coverage, as we see in the earlier slide. Particularly, if we look at each individual test, DB-Gradler produced only 43 new DB states, and these 43 new DB states can cover 33% more DB-dependent branches for one test. This shows that DB-Gradler is efficient in increasing the branch coverage. We also want to mention that the candidates generated by DB-Gradler is likely to pass validation, so we do not waste a lot of time validating invalid DB states. This is especially important when the validation is slow. We compare it with the fuzzing baseline, which randomly fuzzes existing DB states while using the same amount of time. The problem with random fuzzing is that it rarely produces a state that passed the validation check. So most of the time, the base state on invalid DB states. The baseline only increases branch coverage for 2 out of 9 applications, which are much smaller coverage increase. DB-Gradler also finds bugs as a side effect. We use a very simple test oracle for bugs. So when running a test on a new DB state, when the test throws an unhandled exception, which eventually returns a 404 web page, we view it as a bug. With this oracle, we found 26 distinct exceptions, among which 22 are true bugs, and 12 has already been confirmed by the developer. most of them are null bugs where the query result is directly used without checking whether the result is null or not. Based on this observation, we build a baseline to check the null bugs, where we use static analysis to find unchecked query result using the code QL. Compared to dbGuider, this null bug checker has much higher false positive rate, 97% as compared to 15% of dbGuider, mostly due to its limitation in type inference and the lack of constraint analysis. I guess I'm probably running out of time, so I'll stop here. And thanks for listening, and I'm happy to take any questions.
Cool. Thanks a lot for the talk. Yeah, so we have time for some questions. We need to use the mic, so don't just shout. Okay, and while people are still... Oh, there's one here.
Hi, thanks for the presentation. My question is, once you have computed a new valid database configuration, how do you then map that to the test configuration that corresponds to it? So you said that you increase the branch coverage, but then how do I also generate a corresponding test with the proper assertions that will actually utilize that configuration?
Yeah, good point. So here, we don't change the test body. So if you see in the first slide, sorry, it's a little bit slow, let me go here. So we only change the part that populates the database. We use the same test body. So basically, for the overall coverage increase, we just run all the tests with the DB states. So we generate new DB states for each test. And then we kind of aim to increase the, for example, here, this is the checkout, right? And then this is just like a simple checkout web page. So we want to change the database content to simulate, for example, a successful checkout, a successful checkout, and unsuccessful for different reasons, which is determined by different branches in the application. So we use the same test body just to change the database content.
Cool. So there's another question.
Thanks for the great talk. I have a question about the testing throughput. How many tests you can run per minute, per hour, or whatever? And do you have any solution to improve the testing throughput for your application? Thanks.
Yeah, we mentioned in the slides that the test is very slow, taking up to 28 seconds. So this is by the application itself, and then I don't think there's anything we can do with that because the test. Some existing test is already written by the developer, and then it is slow because of the database it is using, and then we cannot say like, okay, you need to change the database to like another because the test is faster. So yeah, because we can only like work around the slow test by say like we try to generate as fewer DB states as possible so that we don't need to run so many tests to achieve the coverage increase. So that's like this is a little bit different from other testing. Sometimes like the test can be very fast, so you can try a lot of options, but not here. Yeah.
So we do have time for one or two more questions, if there are any. Otherwise, maybe let me ask a question. So the goal of extracting these constraints is to generate likely valid database states. So do you have an idea how often you achieve this goal as opposed to generating an invalid database state?
Yeah, so getting the constraint is not, the purpose is only to like have a script to check whether a state is valid or not. So we just have like a different mutation mechanisms so that this mutation mechanisms is likely to produce valid states. So in practically 93% of the states we mutate, we get up by this mutation is valid. So compared to random mutation, just rarely produce a valid state. Okay. So we don't use the script to generate the state, but you only use the validation script to validate.
Okay, yeah, thanks for clarifying. Any other questions? Yeah, okay, final question.
Hi, nice talk. So you said that you have a constraint solver for checking for DB states. I was not very clear on exactly what you meant by that.
It's not a solver. So basically the application itself has some code to check whether a state is valid or not. But this is just like when the data is inserted into the database. So we have like a static analysis to collect this bunch of code scattered in the application and then recompose them into a database state checker.
So what is this DB state? Is it an abstraction of the database or?
Database is just like a database instance. So basically, they are just the tables with tuples in it. So it's like one database instance. We call it a DB state.
Okay, thank you.
Cool. Well, thanks a lot for answering all these questions, and thanks again for the talk.
Okay. Oh, hello everyone. I'm Jinsheng. I'm from National University of Singapore. Today I'm glad to share our work about the test case generation problem in database testing. It's a joint work with my advisor Manuel. We are likely to pass our artifact evaluation and won a distinguished paper award here. Let me get started. Database are widely used to store, retrieve, and manage data, and we have many successful products like MySQL, PostgreSQL, and this database are widely used. For example, for SQLite, it's used in almost every Android phone, every iPhone, and every Chrome. So therefore, any bug has a severe potential consequence. In this work, we have found more than 50 unique previously unknown bugs. To find these bugs, we need Oracle. Oracle to help us to observe the bug, to help us to identify what is the bug. For example, if we want to detect some logic bugs in the database, the logic bug means the incorrect results. Here is the Oracle we use to do that. We call it no-rec. It works as follows. Suppose we have a query. It has a predicate in the where clause. We derive another query where the predicate is put in the select clause. So the two queries should be some semantically relevant. So we will check whether the number of truths of the second query equal to the number of rows in the first query. This should be always true. If we observe some inconsistency, like this, the first one returns one row, while the second one returns an empty result, it indicates there is a bug. However, this Oracle is a runtime component. It can only detect a dynamic execution result. How do we to generate the execution? We require the test case. A test case in database refers to a SQL query and a database state. Then we execute the test case, we get a result, and use Oracle to validate the results. So the problem here we want to solve is how do we to generate some diverse test case to automatically find this kind of bugs. Toward this goal, there are several previous words. The first line of words is generation-based method. It's, for the SQL query, it has a grammar. Here is a grammar for CockroachDB. It specifies how a query should be like. Like in here, we can only specify the keyword all or distinct on the target element after the select keywords. Otherwise, it is an invalid query. So therefore, we can generate some test case based on the grammar. It can generate so many valid test cases, but it's also restricted because we have to restrict to the grammar and have to generate only a small set of valid queries. Several examples like the SQL Smith or SQL Lancer, they all need a grammar and generate many valid test cases. To make the test case more diverse, another kind of word is a mutation-based method, which is typically called code coverage, grayboard fuzzing. However, this method, the mutation is easily to make any valid test case invalid. Any mutation will make the valid query invalid because change any character. Like this, existing word SQLite only achieve around 40% of valid test case. And Another challenge of this method is that code coverage is insufficient to exploit database states. Although we use code coverage as a guidance to generate more and more diverse test cases, in the circular document we found that they already cover 100% of coverage. But can we see there is no bug? We cannot see that, right? Because we still keep finding new bugs. Example here is the SQLite. So to solve this challenge of the previous words, we propose our idea to use the query plan guidance to guide the test case generation. We hope the query plan can help us to cover more and more program behaviors and to automatically find more and more the bugs in the database. Let's look into this idea. Query plan, what is a query plan? A query plan is a tree of operations that represent how the query is executed. Suppose we have input to table T0 and T1. We have a query, select something from the two table. If we want to execute this query, we have to translate to a query plan. Because the query circle is a declarative language, it only specifies your goal without specifying how to get your goal. So to execute your query in a database have to translate to a concrete execution steps and execute it. And we can also manually specify, examine the query plan by a prefix is plan. Here we can add a prefix and get the query plan to see how the database executes the query. Here it will first scan the table T1 with a filter and then join the table T0. Then it gets the results. Definitely query plans are not designed for testing scenario, and it typically exposed by DBMS, and the user may use them for turning the performance, and we want to move its application scenario from the performance tuning to the testing scenario, because it includes many valuable information. It includes this, how to scan table, use the full scan or partial scan, or how to join table, use which algorithm. And this algorithm, this query plan is a high-level abstraction of the internal execution logic, and we can use it as a more efficient feedback to indicate what internal logic has been tested. Based on this insight, we hope we can continually generate more and more queries, and hope they can cover more and more unique and thin query plans, and therefore more bugs found. To investigate whether query plan is suitable for the test case generation as a guidance, we investigate the query plan in the previous found bugs. We have two observations. The first one is they are very diverse. The sum column means the total number of query plans in this test case, and the unique represents the number of unique query plans in this test case. We have found that more than half of the query plans are unique for the previous found bugs. With demonstrate we can cover more and more different query plans to observe different behaviors. A second observation is that they are typically compact and simple, as every length is less than 3. The length refers to the number of operations in a query plan. If more operations in a query plan, it typically means this execution is more complicated. So to achieve this goal, we design our algorithm. Firstly, we reuse the query generation and database generation. They are just the existing method to randomly generate them. And after that, we collect the query plan and maintain a pool to collect the unique query plans and then return back. The important step, if we haven't observed query plan for a certain time, a certain number of iterations, we mutate database state to get a new database state, hoping we can cover more unseen query plan in the following queries. And how to select the mutators, we model it as a multi-unbounded problem and select the most promising one. So overview, we change the state to add new index, and we find a new query plan for the same query, and we are likely to find new bugs. For the evaluation to demonstrate our efficiency, we want to show how many bugs we have found. With the help of our method, we called it QPG. It's a short name of the query plan guidance. We have found more than 50 unique previous unknown bugs as of last year, August. Several bugs have been hidden for more than 6 years. To demonstrate the efficiency of our method, we are the only first one to find them. Like this one in the circle line, this bug goes back to almost 8 years ago. And our method is also very general to find all kinds of bugs, crash, error, and logic. Since we have found more bugs, we also want to demonstrate whether we can cover more unique query plans. To demonstrate the efficiency of our algorithm, our evaluation shows that we cover up to 400 times more unique query plans than a naive random generation method. So in conclusion, we here discuss the possible to use query plan and guidance and do a small-scale study and full-scale approach. The evaluation shows our methods that the query plan can efficiently guide test case generation in a black box mode. Our code and I also open source here. Welcome to get more information here. I'm here. I'm welcome more questions.
Cool. Thanks a lot. Questions?
Thanks for the great talk and also the great work. My question is, how do you check the similarity between the query plan? You said that you can count like how many unique query plan that you can find, right? But how do you compare the query plan?
You mean how to distinguish the different query plan? Oh, yeah. Here we can see several query plans. We have some table names and the Zhong algorithm. We will remove the table name, the view name, remove some of the very customized name, and otherwise we simply compare other components as to distinguish a unique query plan.
Okay, I see. Thanks.
Hello, I have a basic question about the query plan. So what aspects can affect a query plan? For example, the state of a database, can it affect the query plan? Or does the input query, can it affect the execution of the query plan? So what kind of aspects will affect the actual query plan?
Yeah, both. Actually, the answer is both. Both the database state and the input query can affect the query plan. For example, here, for the same query, if we add a new index to the table, the query plan will be quite different, even for the same query, because we can use the index to speed up the execution speed. So for each execution, it will first check what you want to get from the input query, and then check the database state to decide the most efficient query plan.
So I have a follow-up on that. So in your approach, do you only generate the query, or do you also change the database?
Oh, exactly. The good point, yes. In principle, as I said, both the input query and database state will affect the query plan. But here, we only mutate the database state while randomly generate the input query, because it's based on our experiment that the input query is easily to get invalid if we want to mutate it. Well, we avoid it. We just to mutate the database state to make it more efficient to generate some more diverse query plans.
Cool. So we have time for one final question.
I also have a follow-up on the two previous questions. Is the output from explain the query plan before or after the optimizer is run over the input query? And then follow-up to that, is that stable across database implementations?
Actually, I can first answer your last question. It's not stable across DBMS. If you can compare the query plan in different databases, they are quite different. So we can see why this DBMS is faster while that one is slower. Yeah. And sorry, what's your first question?
I actually just meant more so that that the output from explain is actually going to accurately represent what the database is actually going to execute. You know, if you're getting pre-optimizer output, then it doesn't reflect the actual query plan that's going to be executed.
Yeah, so first you give the query and the database optimize your query and get this query plan. But after you get the query plan, it's really executed. So the query plan is before the execution, but after the optimization.
Cool. Well, thanks a lot for the talk and for answering all the questions.
Thanks.
Good morning, everybody. My name is Jiansen from the University of Chinese Academy of Science. Today, I'm going to talk our work on testing database system via differential query execution. Database management systems are widely used to restore and manipulate data. According to the DBMS ranking, 7 of the 10 most popular DBMS are relational, like MySQL, PostgreSQL, and SQLite. Relational DBMS use SQL to retrieve and manipulate data. For example, we can use select to retrieve data and update delete to manipulate data. Incorrect implementations of DBMS can cause logic bugs. For select statement, it can generate incorrect query results, for example, miss a row. For update, it can generate incorrect database states, for example, update partial table data. For delete statement, it can generate incorrect database states, for example, delete one row. We need an oracle to identify these bugs. There are some approaches to detect bugs in DBMS. Some approaches like Salesmith and Squirrel, they detect crash bugs. And some approaches detect logic bugs in select statements, like Rex, PQS, NoRec, and TOP. However, these approaches cannot detect logic bugs in update and delete statements. We observe that in DBMS, SQL statements utilize predicts to specify which row to manipulate. In this example, for select, the predictor specifies the third row to return. For update, the predictor specifies the second row to change, and for delete, the predictor specifies the first row to remove. When having the same predictor, select, update, and delete statement should access the same rows. In this example, they should all manipulate the third row. Thus, select return the third row, update and delete manipulate the third row. However, a DBMS usually adopts different implementations for predict evaluation in select, update, and delete statements. In this example, for select, MySQL evaluates the value of greatest function in the predict. While for delete, it only checks the column C1 and C2 is null or not without evaluating the expression. And such inconsistent implementation may cause logic bugs. Inspired by the key observation, we propose differential query execution, short for DQE, to detect logic bugs in select, update, and delete statements. The core idea is that, given a select, update, delete statements with the same predict, we compare their access rows. If they access different rows, DQE reveals a bug in the DBMS. The key challenge of DQE is to automatically obtain the access rows for each statement. For select statements, we need a column to uniquely identify each row. In this example, we cannot figure out it is the first or third row to return. To solve this problem, we design a column row ID to uniquely identify each row. In this example, given a table T1, we first add the column row ID, and then rewrite the select statement without changing its execution schematic. We then execute the select statement and obtain the row ID from its query result. In this case, the third row is returned. For update, we need to mark which rows are updated. In this example, we cannot figure out which rows are updated because there is no change in the table content after executing the update statement. To solve this problem, we design a column updated to mark which rows are manipulated. Given a table T1, we first add the row ID and then add the column updated. We rewrite the update statement by appending the updated equal to true in its updating field without changing its schematic. After executing update statement, we split row ID from its execution result with condition updated equal to true. And in this example, the third row is updated. For delete statements, we use the column row ID to obtain its delete rows. Given a table T1 delete statement, we first add the row ID and execute the delete statement. We compare the row ID in table T1 before and after executing the delete statement. The difference is the delete rows of the delete statement. In this case, the third row is deleted. When selecting from multiple tables, we add row ID to each table and rewrite the select statement. After that, we execute the new select statement and obtain the row ID from its query result. Because of the joint operation, row ID can appear more than once, so we remove the duplicate row IDs if necessary. When updating multiple tables, we add the row ID and update it to each table and rewrite the update statements. After that, we execute the new update statements and obtain the row ID from each table and combine them together. When we get these access rows, we compare them. If they access different rows, DQ will reveal a logic bug. When these statements rise an errors, we compare the error message. Since a DBMS usually adopts a differential strategy to evaluate predicts in select, update, and delete statements, so we do not compare their access rows. For example, in this case, VariDB evaluates the predict in select statement and writes a warning. It continues to execute and finally return all rows. For update, it writes an error and stops the update operation and roll back. As a result, no row is updated. Similarly, in the delete, it also writes an error and the result, no row is deleted. However, this error message should be seen. If this statement writes different errors, for example, in the select statement, it writes an error message, we can detect this kind of bugs. In another example, when select statement should write an error, but it does not, we can also detect this kind of bugs. Moreover, update and delete can write their specific errors when violating table constraint. In this example, when updating a table T1 with a unique column C1 to an existing value, an update-specific error is returned. And in this example, updated does not change any rows, and we ignore this error. And for select and delete statements, this do not write the same kind of errors, so we do not compare the update with the select and the delete statements. To evaluate the effectiveness, we try to answer in the following two questions. What logic bugs can DQE detect in real-world DBMS? And how many bugs detected by DQE can be found by existing approaches? We focus on file widely used DBMS. According to the DB engines ranking, MySQL, SQLite, and MariaDB are the most popular DBMS. According to the GitHub stars, CockroachDB and TiDB are the most popular relational DBMS. In total, we have found 50 bugs. 41 bugs are confirmed as new bugs, and 11 have been fixed. For the 41 confirmed bugs, we further analyze their bugging trigger statements. There are 21 bugs triggered by the select statements, and 20 bugs triggered by update or delete statements. We further compare DQE with the existing works, including PQS, NORAC, and TLP. As a result, they cannot detect the 20 bugs triggered by the update and delete statements. For the remaining 21 bugs triggered by select statements do not violate their oracles. To summary, inspired by the key observation that DBMS utilizes predicts to specify which row to manipulate with proposed DQE to compare their access rows. For optimally obtain the access rows, we design two-column update and row ID. We evaluate DQE on file widely used DBMS. The result indicates the effectiveness of DQE. We make our tool publicly at GitHub. For more information, you can review our paper. Thanks for listening.
Thanks a lot for the talk. Yeah, time for questions. No one yet? Okay, let me get started. So did you see any relationship between the bugs that are triggered and the complexity of the queries, or the complexity of the predicates, or anything like this? So basically, when do these bugs happen?
This happens mainly caused by the predicts and different statements evaluate the predicts in different ways. Such inconsistency may cause bugs.
Mm-hmm. Yeah, but is it more likely to have such bugs in databases when you query these databases with very complex predicates, or is it independent of the complexity of the predicates, for example?
Actually, simple predicate can also trigger bugs, and the complexity may tend to trigger bugs because it's complexity.
Mm-hmm. Okay.
So I have one more question. So is it possible that the select query itself returns different results at different times, or is it at least deterministic?
Actually, this should not happen because the cycle is executed based on the relation algebra. It's a set algebra. They should specify the same rows according to the predict. This is not a law because this is deterministic. They should be the same.
I see.
Just a follow-up question, and could you explain how complex are your generated queries, like the length of the predicates, the number of rows that you accessed, or some other metrics? Yeah, in terms of, could you explain the complexity of the queries? Yeah.
Do you mean how we generate the database or queries?
Well, maybe both.
Okay. Actually, there are many existing words for database and query generation. We adopt the sequencer to generate our database and the query. Yes. And they do a great work for this both two functions.
Then the complexity, how complex are those queries? Like
how complex?
Yeah.
Yes, we mainly focus on the complexity of the predict. Yeah. Because of the predict consists of the operator and the function. We recursively to generate based on the AST. We set the length of the AST. For example, it's 3-hour experiment. We recursively to generate the predict. And for the select field, update field is simply because it only sets some columns or the assignments.
Yeah. Yes. Okay. Thank you.
Any final question? Yeah.
I hear that you mentioned you based on sequencer, right?
Yes.
Do you consider to pull your word to sequencer, push your word to submit to sequencer merge to?
I wish. I think I can make some contributions. Yes.
Great. All right. Thanks a lot for answering the questions and the talk again.
Yes. Thank you.
Hello everyone, my name is Min and I'm a PhD student from Tianjin University, supervised by Junjie Chen. Today I'm excited to present our recent work on chip design implementation testing. This work was done by Tianjin University and Huawei. Nowadays, chip has been widely used in our daily life. From mobile phone to airplane, chip is everywhere. However, chip can also suffer from defects. For example, a chip defect cost over $400 million financial loss for the company Intel. So chip testing is very important. And since we are the first study on chip design implementation testing from software engineering community, so I'm going to spend a little bit more time on the background. First, the chip design company will collect the requirements from their customers and make the chip specifications. Then the development team will implement the chip design using hardware description language. At this stage, the chip design implementation is a kind of program as general software, and we call it the CDI. Then the testing team will test the CDI, and the well-tested CDI will then be pushed into physical design and finally put into production. And in this paper, we focus on CDI testing. Here, the inputs of CDI aim to simulate user requests during the chip use and can trigger some functionalities. And the inputs require to set the values for a set of variables. And the variables are responsible to control simulated user requests. And also there are constraints among the variables. And if one input violates the constraints, it will be changed by the constraint checker in the simulation environment.
In code coverage is often used to measure test adequacy in traditional softwares, but it's not enough for CDR testing because only with code coverage, we cannot know that whether there are non-implemented functionalities, and we cannot know that whether all possible combinations of inputs has been explored by the given test suite. So in CDR testing, the testers define functionality points. It measures whether a specific functionality is tested by the given test suite, and similar functionality points belong to the same functionality group, and the functional coverage measures the percentage of covered functionality points during testing. So with functional coverage, we can know that whether there are untested functionalities, and we can know the coverage of CDR's design intent. But achieving full functional coverage can be really, really difficult. For example, covering the last 10% of functionality points can take the most of the testing time, and we call such hard to cover functionality points the last mile functionality points. And the ultimate goal of CDR testing is to efficiently achieve high last mile functional coverage. But there are two challenges in CDR testing. First, the input space of CDR is really, really huge. And secondly, there are constraints among the variables, but we cannot assess the variables because in CDR testing, we prefer nearly black box testing methods because the testing teams and the developing teams, they are supposed to be independent. So to address the first challenge, we identify the most relevant variables to a specific functionality group to reduce the input search space. And to address the second challenge, we learn the constraints among the variables to generate the valid test inputs. Here's the overview of our approach. We first randomly generate the test inputs to cover the easy-to-cover functionality points and expose the last-mile functionality points. And after the random test generation, we can get the functionality groups that remains uncovered, and we can get the valid test inputs. The valid test inputs are checked by the constraint checker in the simulation environment, and they are the training data for the following two components. The first component is designed to identify the most relevant variables to a specific functionality group to reduce the search space. And the second component is designed to learn the constraints. And we use GAN to learn the constraints. And we use the generator to generate the valid test inputs. And based on that, we design a heuristic-based strategy for the test generation. Here's the details. Firstly, we model the relevant variable identification task as a multi-label classification problem for each valid test input. We use the functionality cover status to label it. And that is, we mark the covered point as 1, and we mark the uncovered point as 0. And then we use the inputs and the labels to train a random forest. And the random forest is often used in feature selection scenario. It calculates the feature importance score for each feature during training the classifier, and the feature importance score denotes whether a variable is important to cover a specific functionality point. And we then rank the variables according to their feature importance scores, and we adopt the top key variables as the most relevant variables. And in our paper, we set the key to 50, and we also studied the influence of the parameters. And in constraint learning, we use GAN to learn the implicit constraints. And GAN has two parts, the generator and the discriminator. The generator takes random noise as input and generates a fake sample. And then the fake sample is combined with the valid test input, and they are then passed into the discriminator. The discriminator is trained to distinguish whether the data is real or fake, and the generator is trained to fool the discriminator. And then after training, the generator is able to generate test inputs that satisfy the constraints more than the random test input. But we find that the test inputs generated by the GAN are less diverse. This is as known as the mode collapse in GAN. So to address it, we design a heuristic-based test generation. For each functionality group, we sample M settings for the relevant variables. But how to set the settings for the rest variables? We use the generator to generate an valid test inputs as candidates. Then for each explored setting, we calculate the similarity between it and the settings on those key relevant variables in each candidate. And we select the candidate with the largest similarity. And we then combine the explored setting and the settings on the rest variables to combine a new test input. So it's more likely to be valid. And then the test inputs are passed into simulation. And we can get the functional coverage, and we repeat this process until we achieve full functional coverage, or we meet the termination condition. And we conducted our study on 2 industrial CDS in Huawei due to the company policy. We simply call it Module A and Module B and hide their real name. And we randomly generate the test inputs to expose the last mile functionality points. And we have 3 baselines. The first, the random testing is widely used in practice. And the second one, a DL-based approach. It builds a DE model to filter out test inputs on the basis of random testing. And the third one is a J-based approach. And the fitness function is said to be the number of covered last mile functionality points. And we have 2 measurements. And in RQ1, we studied the overall effectiveness of LMT in the following figure. The x-axis represents the number of used test inputs, and the y-axis represents the number of covered last mile functionality points. And we can see that the LMT can achieve higher last mile functional coverage than the baselines, and it can also significantly save the testing time when compared with the baseline and when they achieve the same functional coverage. And we also studied the contribution of each component in LMT. And we built 2 variants. The first, LMT no RF, it drops the random forest in LMT and randomly select the relevant variables. And the second one is LMT no GAN. It drops the GAN in LMT and randomly generates the candidates. And we can see that both components contribute to LMT and that their combination can make the best performance. And here are the takeaway message of my talk. Currently, LMT has been deployed on more industrial CDS in Huawei as the standard testing techniques. And thank you for your attention. Any questions? Welcome.
Thanks a lot. Yeah, time for questions.
So you said GANs have low diversity. I mean, the outputs provided for GAN have low diversity. Why is the case?
So you are talking about the valid test input generated by the pure GAN, and this is the model collapse. You are talking about this one?
Yes.
Okay. Yeah, we find that ideally, if GAN can generate the test input that satisfy the constraint and is very diverse, so we can directly use the test input to test the CDI. But we find that GAN will he thinks that some inputs can constrain can satisfy a kind of constraint, so it directly only generated the test input that only satisfy only some part of the constraint. So he will generate.
So perhaps is it because the inputs that were used to train the GAN were not diverse enough?
I think it's not enough because we use the grid search during the training. We choose the best performance. Yes, we chose the checkpoint with the best performance. I think it's not about the training, the training. Okay, yeah. Sure. Thanks. And then the mode collapse is well-known in philosophy in machine learning. Yeah. Thank you.
I saw some other question. Yeah.
So it's a question probably definitely out of scope, but I'm just curious, you know, when testing chips, it's really tricky because sometimes like something happens during runtime, maybe 2 + 2 = 5. I'm just wondering if you have any thoughts or know any work about that.
Okay.
Super tricky situations.
Okay, good questions. So you are talking about the logical bugs in chips? Yes, but yes, there are many topics in CDI testing because, for example, the logic bug you mentioned. But in this paper, we don't care about the logic bug. We only care about the functional character that we have implemented all the functionalities. We have tested all the combination of input, because if you miss the one functionalities and you have put it into production and the chip is on your mobile phone, it's too late to change it. So we only care about the functional character. But testing the logic bugs is very important. And there are many topics. Yeah. Yeah, thank you.
Yeah, I had a question on your results. So could you go back 1 or 2 slides when you had these graphs? Yeah. So this is all the x-axis is always the number of test inputs. Did you also measure the effectiveness over the time that you need to generate these inputs?
This is a slide about when we compare the time, I say the MMT significance as the testing time. We have include the training time and the time used on random forest, but for random testing, it only includes the testing time. Yeah, because LMT needs the random forest and needs gain, so we need time to train it. But I have included the time into the comparison.
Oh, okay. So this is not what the plots are showing, right?
Yeah.
This is a different result that is in the paper. Okay, got it. Cool. Any other questions? So since we have some time left, maybe a very general question. So you're testing chips, but it seems a lot of the ideas you're using here could also be applied to some kinds of software, where you basically want to do black box testing of some piece of software that also takes some variables as the input. So is there anything that software testing can learn from your work, or maybe that your work could or has learned from software testing?
Yeah, I think this kind of approach can apply to other softwares that they share the common characteristics. Because if a software have the complex input and the larger input space, and they are the very strict constraints on the variables, I think it can be applied to it. But yeah.
Okay, cool. Thanks. Any final question? Yep.
What was the functionality of the chips you were testing? What were they intended to actually do?
So you are talking about the functionalities used in the subject in my paper?
Yeah, of the chips, I guess. So basically, your module A and module B.
Okay.
What was their function?
I think I can answer part of the question, because due to the company policy, I can't see much more details. But for example, the chips are used in network. So there are some functionalities control whether we should turn on the 5G network, or whether we should turn off the 5G network of the signals passed to the chips themselves.
All right. Yeah, cool. Let's thank the speaker again.
Thank you very much.
Hello, everyone. I'm Yang Rui from University of Chinese Academy of Sciences. It's my honor to be here and talk about our work, randomized differential testing of RDF stores. We call the graph database systems that are built on the RDF graph model as RDF stores. The representative RDF stores include MarkLogic, Apache Gina, RDF4j, and so on. They play a significant role in knowledge graphs and semantic web. RDF stores utilize RDF graph model to store graph data. This graph shows the personal information of 3 persons and their social relationship. RDF stores utilize Sparkle as their standardized query language. This example queries the given name and age of the person who is now 20. Similar to other database systems, incorrect implementations of RDF stores can introduce logic bugs that result in an incorrect query result for a given query. This is a logic bug found in MarkLogic, we retrieve the RDF triple by a filter expression, which should be evaluated into true. However, MarkLogic mistakenly returns an empty result because the expression is evaluated into false due to demical overflow. Existing database system testing approaches detect logic bugs in relational database management systems and Gremlin-based or Cepher-based graph database systems, which adopt the labeled property graph model. However, RDF stores adopt totally different RDF models and query syntaxes. Existing approaches cannot be directly applied on RDF stores. We propose a randomized differential testing technique, RD-square, to find bugs in RDF stores. First, we generate an RDF graph and write it into multiple target RDF stores. Then we generate Sparkle queries. Finally, we run a Sparkle query on multiple target RDF stores, get the query result, and reveal discrepancies. An RDF graph consists of a set of RDF triples. An RDF triple consists of a subject, a predicate, and an object. We first randomly generate basic elements. Then we randomly select corresponding data for subject, predicate, and object to construct an RDF triple. Following this approach, we can generate more RDF triples. To generate syntactically correct and valid Sparkle queries, we build abstract syntax trees. To generate the triple pattern in where clause, we first randomly generate variables and then randomly bind them to subject, predicate, or object. The subject, predicate, and object in a triple pattern can be generated randomly or be selected from the RDF graph. It can increase the possibility of returning non-empty query results. We generate a filter expression by building an expression tree. The select clause is generated by randomly selecting several variables existing in the where clause. We adopt differential testing to find discrepancies among multiple target RDF stores. However, different RDF stores usually have their own storage and query result formats, such as the ID of the same blank node is different in different RDF stores. So how can we compare them? To address it, we need to unify formats of these IDs. We first extract actual IDs of blank nodes in each RDF store. Then we generate a unique ID for each blank node. In this way, we can convert IDs in different formats into unified IDs. To use RD-square, we first execute the command to run it and obtain discrepancy reports. Then we analyze discrepancies to identify bugs. We evaluate RD-square on 3 widely used RDF stores, MarkLogic, Apache Gina, and RDF4J. We find 5 logic bugs among them. 2 bugs have been confirmed, and the remaining 3 bugs are considered as intended behaviors due to different implementations. In conclusion, we propose a randomized differential testing approach of RDF stores to find logic bugs and have detected 5 logic bugs. Our tool can be found in GitHub. That's all. Thanks for listening.
Thanks a lot for the talk. Yeah, time for questions. Maybe let me start with one. So did you see any false positives? So sometimes in differential testing, you see differences. And then if you look very closely, it turns out that they are actually okay for some reason. So did you see any of these cases?
Sorry, could you please?
Did you see any false positives? So differences in behavior between 2 RDF stores that are legitimate? So not a bug?
Do you mean, is there any bugs that are very different from other bugs in the RDF stores?
No, I mean, if you so the bugs that you find, I guess, are differences between the different RDF stores, right? So you run a query and you get some result. And if the result is different in this store than in that store, then you say, hey, that's a bug.
Oh,
right?
yeah.
So did you see any cases where the results are different, but it's not a bug? So a false positive.
Oh, yeah. Because different RDF stores may have different implementations. So they may, such as they may use different numeric representative of same number. So like this bug, they may consider it as intended behaviors due to their different implementations.
Mm-hmm. So did you see any such cases in your evaluation?
Yeah, we have found some bugs like this, and the developers considered it as intended behaviors, not a bug.
Yeah, okay. Any other questions? All right, well, let's thank the speaker again.
Thank you.
And the last talk will be given again by the first speaker because he did such an awesome job. So it's a journal first paper called Boosting Compiler Testing via Compiler Optimization Exploration. And yeah, the talk is given again by Chenyao. So.
Hello, I'm back again. And I give the first presentation and answer the last. Hello everyone, my name is Chenyao from Tianjin University, and I'm going to be a doctoral student supervised by Professor Jinsheng. And I'll present our new work on compiler testing, boosting compiler testing via the compiler optimization exploration. Detecting optimization bugs needs to consider two main factors, the test program and the optimization. The test program is the input of compiler, and optimization is controlled by both optimization level and optimization flags. The optimization level can be seen as a sequence of the optimization flags, and the optimization flags is the option that controls the corresponding optimization to be closed or open. However, existing works mainly focus on the test programs and the test compiler under several predefined optimization levels. So there exists a huge optimization space has not been explored for compiler testing. And to better understand the influence of optimization on compiler testing, we conduct the following study. In this study, we will compare the optimization levels and the randomly constructed optimizations. To construct the optimizations, we select a pair of the higher level and a lower level. And we identify the differential set between the higher and the lower level. And we firstly open all the optimizations in the higher level and randomly close the optimizations in the differential set to construct the random optimization. And here are the pairs we used to construct the optimization. And this is the result of the number of bug triggering test programs. We can find that a number of test programs cannot trigger a compiler bug under the predefined optimization levels, but indeed trigger bugs under the random optimization. So it's necessary for each test program to explore the compiler optimization to boost compiler testing. And this is the result between the optimization level and each pair of optimizations. We can find that many higher levels that should open much more optimization, however, find fewer bugs than the optimization come from to the related pairs. So it demonstrates the inhibition effect of optimization for bug detection. And this is the result of the average size of minimal bug triggering optimization combination and a bug case we reported to LLVM. We can find that there are usually more than one optimization in the minimal bug triggering optimization combination, and even when the root cause is only one optimization. So it demonstrates the promotion effect of the optimization for bug triggering. And through the above three findings, and to make better use of optimization on compiler testing, the key challenge is how to select the proper optimization for each given test program. Our solution is that to use the machine learning to model the relationship between the optimization, the test program, and the bug triggering. We built a bug triggering prediction model and sample diverse candidates to predict. So we propose our approach call-test. Call-test consists of 2 steps, the model training and the testing, and the model using. The model training aims to obtain a bug triggering prediction model that can predict the bug triggering probability for each pair of the optimization and the test program. We extract, combine, and normalize the optimization feature and the test program feature as the train feature, and we collect the test result on the historical version of bugs as the train label to obtain this prediction model. And the testing process aims to select a set of optimizations that have larger bug triggering probabilities for each test program. However, it's impossible for us to predict all optimizations for each given test program, so we should sample some candidates to predict. And our solution is to sample some candidates via the diversity and use the masks and the exclusive OR to accelerate the sampling process. And then we'll put each pair of the optimization candidates and the program feature into the model to predict. And finally, top K optimization with the largest bug triggering probability would be selected for compiler testing. And to evaluate the effectiveness of call-test, we compared call-test and baselines on the historical version of compilers and use call-test to test the trunk version of GCC and LLVM. That's all my talk. Thanks for your attention.
Thanks a lot. Questions?
Hi, nice talk. So did you have, how did you get enough data to train this prediction model? How did you get enough data to train this prediction model? Are there so many bugs in compilers?
Do you mean the duplicate?
For the prediction model that you were building? The training data for that?
Training data? We collect the training data on the historical version of compilers. And we use the randomly constructed optimization and the test program generated by CSMIS to test the historical version of compilers and collect the train feature and the train label.
So how many instances of failures did you have in the training data?
About 2,000.
Okay.
And about 600 are the buggy instance, and the others are non-buggy.
Maybe
the train version is showed here before the row.
You have a follow-up on this learning idea. So when you train the model on past bugs, then it's going to be really good at telling you which optimization flags will trigger the past bugs, but maybe they are not. The model is not good at predicting what helps you to find new bugs. So how do you make sure that the model actually also helps you to find new bugs?
Did you mean whether we filtered out the bugs that have not been fixed?
No, I mean, if you train the model to predict how to find the old bugs, the known bugs, why is this model actually good at helping you to find new bugs?
First, for the optimizations that have not appeared in the historical version, we select the random. We use the random value of this optimization. And so for the new optimization, we can also find some bugs. And for the optimization in the historical version, we will use the learned experience.
Okay. Cool. Yep.
Are you able to use the same prediction model across the two compiler implementations?
Across the two? For example, the first row and the second row?
So just GCC versus LLVM, I mean, I would imagine that they have different configurations of optimization options between the two.
That's different.
So you're able to use the same model, or you have to use different models that you've trained on different data?
No. for each version of compilers, we must train two models to satisfy the optimization, because they are different from the across the different compilers, the versions.
Cool. Any other questions? Looks like everybody's ready for lunch. All right. Well, then let's thank the speaker again.
Thank you.
Yeah, thanks for joining this session. Thanks for all the questions, and enjoy the lunch.